You start the recording, right? Yeah. Okay. So today's speaker is Yevgeny Bar Lev, so Yevgeny did his PhD at the Technion in Israel. Then he went to Columbia. Then he was for a year in Weizmann, and now he's an assistant professor or associate, or whatever it is, in Ben Gurion. And he's going to talk to us about, well, you see the title, long-range interacting quantum systems, which is sort of one of his areas of specialty. And let me say that, if people want, they can switch on their cameras, because this gives the speaker sort of the sense that there are live human beings at the end of this. But, feel free not to if you don't want. I'm just saying. So yeah, Evgeny, please finish, by the way, on the hour if people want to leave, and then we can continue discussing. Okay?
Okay, good. So thanks, Achilles, from the introduction. Thank you all for the invitation for this nice seminar. Today I'm going to talk to you about transport and long-range interacting quantum systems. This is a work which was done by me and Benedict Kloss, who is a PhD student in Columbia University. And the outline of the talk is as following. We start with a short introduction, and then we will discuss about transport and information propagation in clean long-range spin chains. And in the second part of the talk, we are going to add some dirt and talk about disordered systems, and also discuss transport and possibly information propagation in such systems. And just to understand why long range is even interesting, let's start with that. So the fundamental interactions are long range, as we all know. Gravity, electromagnetic interaction are described by this famous formula. This is all nice, but most of the time we have actually, the interactions are actually behaving quite differently. So in some cases, the interaction behave in a mean field-like behavior, or all-to-all interactions. This happens in physical situations like quantum dots or VCS. This is the case of alpha equals 0 in this notation. Okay, so alpha is the range, controls the range of the interaction. On the other extreme, we have local interactions, and this happens, for example, in metals when the Coulomb interaction is screened by the high density carriers. And there are also cases, so this corresponds for alpha goes to infinity. And there are also cases where which live in between, and this is what I'm going to call long range in this context. And they describe a lot of interesting cases of interactions in semiconductors, dipolar interactions, or all van der Waals interactions. Such interactions occur in a number, so this is what we are going to talk about today. And they occur in a number of interesting physical systems like trap irons, Rydbergs, nitrogen bicassette centers, and diamonds. And they're also interesting theoretically, because, for example, for interactions which are quite long range, such that this alpha is smaller than the dimension of the system, then conventional thermodynamics doesn't apply, just because the Hamiltonian stops being extensive. There is a whole chapter on physics dealing with that. We are not going to discuss actually this regime in this talk. And another interesting physics which occurs, and that's we are going to talk about here, is that when you have long-range interactions, long hops of energy or particles can happen in the system, and this might possibly create some interesting transport in the system. So the subject or the motivation of this study, or a number of studies, is what is the nature of the transport information spreading in systems which has long-range interactions. So how are we going to characterize the transport? So we are going to mostly talk about spin systems. So we are going to study transport of spin excitations. So in terms of a formula, this is just described by a two-point correlation function of the spin. In terms of a cartoon, one can look on this spin excitation as some perturbation of the density, and this perturbation of the density spreads in space as a function of time. And we can measure the spreading of this excitation by measuring the width of the excitation as a function of time, which is corresponding to this quantity here, and I'm going to call it mean square displacement. This quantity has we can characterize this quantity even further by defining a time-dependent diffusion coefficient, which is just a time derivative of this quantity. And this time-dependent diffusion coefficient has a number of interesting cases. So the most common case is a diffusive behavior. This is when this time-dependent diffusion coefficient converges in a long time limit to just the regular diffusion coefficient, as one would calculate using Kubo relations. And there are two other interesting regimes when this time-dependent diffusion coefficient converges to 0 in the long time range. This corresponds to subdiffusive transport or localization. And another extreme case is when this diffusion coefficient diverges, and this is normally characterized to superdiffusive or even ballistic transport. So, so what is the conventional wisdom? So the conventional wisdom is that if you take a generic system, by generic I mean a system which doesn't have any specific symmetries, it's not integrable, and it also doesn't lie too close to 0 temperature. So this kind of system will exhibit diffusive transport. And if I plot the spreading of the spin density on this plane of space and time, I'm going to see this profile when the time depends, like x squared. So the main question that we are going to ask here is, can we have a different dynamical behavior? And the corner case that we are going to consider is the long range, of course, what the long range can do for us here. So it is very natural to expect when you add long range hoppings or interactions is that you can have a faster than diffusive transport. There was a question, I think.
Yeah, so the three sort of broad categories that you defined, are there analogs of those if the quantity that you're looking at is not globally conserved?
Well, when the quantity is not conserved, I don't know how to define transport. So,
but you can still define some kind of a correlation function in space-time.
Yeah, sure. You can define that, and we are going to talk about information spreading, which is not conserved.
Okay.
But I wouldn't call it transport. So this part is about transport. So this is conserved quantities, but we are going to talk about also non-conserved quantities.
Okay. Yeah.
Okay. So in order to understand that, it is useful to recall what one knows about classical systems. So for classical systems, there is a situation which is called Levy flights. And in this situation, so if one have a walker which performs a random walk in a two-dimensional, three-dimensional space, and the jumps, so the location of the walker is just the sum of the jumps, and we have a situation where the the second moment of this length of each jump is finite, then of course by looking on this equation by the just by the central limit theorem, we understand that this corresponds to a normal distribution. So x is distributed normally, and then we have just regular diffusion. On the other hand, we know then this when this is not satisfied, namely the length of each jump can be quite long, then the central limit theorem doesn't hold, at least not in a regular way. And we can have some other kind of transport, and this is exactly what happens in the regime where the distribution of the jumps has a tail, which is long length, for these values of alpha. So we can see that indeed the second moment diverges, and one can calculate still the distribution of x. So it's not Gaussian, it has now tails which decay exactly like the distribution of the jumps. The moments, knowing the tails, one can calculate the moments, and they behave in such a way. But what is interesting here is that not all the moments are finite, only the smaller moments, so moments smaller than some value, are finite, and above this value, the moments are infinite. And again, we regain diffusion when the range, when the tail decays sufficiently fast. So for alpha, in this case, is larger than 3/2. We regain diffusion again just because the central limit theorem starts to hold, and then all the moments are again finite. So this is what we know about classical systems. Now I'm abusing a little bit of notation here, and I'm calling it quantum Levy flights. So now we want to talk about quantum systems. There isn't an abuse notation because in the literature some people use quantum Levy flights for other things, so it's not very good way. But in any case, what I'm doing here is some naive calculation, which is based just on one particle. So it's not so it's really naive and really based on one particle, and it's supposed to give us some initial direction or intuition of what to expect. So what I'm doing here is I'm calculating the probability of a jump of a particle, of a quantum particle, to jump a certain length L. Okay, and this is just given by this propagator. So I start at site J, and I want to go to the site I, which is L apart, and I have just this regular propagation. And if the time step is sufficiently small, I can expand this, and I get this this behavior. And now, if I recall that the Hamiltonian has a range of 1 over L to the power of alpha, then I get this simple relation. So apparently, we see that the probability, even for quantum systems, to jump far is it has a heavy tail. Also, it has a heavy tail like in the classical system, so we can predict that it's going to behave something similarly to a classical system, namely, we are going to have diffusion for alpha larger than 3/2. We are going to have super diffusion in this regime. I'm not going to speak about this regime in field here. And I'm also not going to speak about this regime where thermodynamics fails here. So mostly we are going to speak from 1 until infinity. And what we are going to see in the talk is that it's actually not entirely correct. So this part will have to be adjusted a little bit for quantum systems. So this is a fine prediction, but not too good. So let's start with transport and clean long-range spin systems. And to study this, we use numerically exact methods. I'm going to show you the system now. So the Hamiltonian that we study here, this is the model Hamiltonian, is a spin chain. For a second, you can ignore from this term. If you want to understand why this term exists, you can ask me at the end of the talk. So let's concentrate on this term only. So basically, we have a flip-flop term which decays as a long range, okay, with this power alpha. And we studied this model numerically using what is called matrix product operator time-dependent variable perturbation, I think. No, I forgot the P. Oh, okay, disgrace. Anyway,
Principle.
Say it again.
Principle.
Principle. Thanks to that, you're a miracle. So so this is this method here, and the method is exact. Namely, we can converge it as a function of this parameter, the bond dimension, and this is what was done. The advantage of this method is that it can treat quite large system sizes, as you can see, 200 sites. We can do even larger system sizes. The disadvantage is, because this is a matrix product state-based method, is that you can see that the times are pretty embarrassing. But I will try to claim carefully that although the times are embarrassing in long-range systems, one can actually say something useful even for these shorter times, because the dynamics is very fast. But here for what we start, I don't need to be so cautious. So what you see here is the density profile of the magnetization as a function of space. Now, since it is symmetric, you only see the positive part of the x-axis, and it is plotted on a log-log scale. And the reason it's plotted on the log scale is for you to realize that that there is indeed a power law tail here. And to see it more precisely, what we did is we calculated a log derivative of this graph on the right panel here. And you see that indeed for power law expected to converge to a constant value, and that's not extremely convincingly, but somehow convincingly, you see that it converges to a value which is designed by this dashed lines, and I'm going to try to convince you even more why this makes sense. So how I'm going
Can I ask something?
Yes, yes.
So is this at the final time? Is it just a snapshot? I mean, at the final time, this is what you're plotting?
Yeah, this is a time too. So this is not very long time. It doesn't change much this behavior as a function of time. So this is one way to sort of say that this time is not too short. Is when even for the very short times that you take, like really short, you're going to see this tail. And if you change the time to 1, 2, as small as you can, this tail doesn't change much. Okay, so it's always there. So now we plot this. So what we plot here, so we extract this exponent, which we call gamma. So this is this just value of this power law. And I remind you what is expected. So we would expect by the naive predictions that this gamma is just going to be 2 alpha, 2 times alpha. So let's see if this happens. So we plot gamma as a function of alpha, which is the range of the interaction. And what you see here is different ranges of fitting that we do. This is different length scales. And this is plotted here by these red lines. And you see that when you go to larger and larger systems, it indeed appears to converge, although it's still quite far, I must say. But it appears to converge to this predicted by theory value of 2 alpha, gamma equal to alpha. In order to test it even more rigorously, what we did is we took a non-interacting system, which is just fermions which can hop in this way with a long range. And this system, of course, we can simulate to any time we want and for quite big system sizes. And this is what you see by this yellow line. So you see that you see by the yellow line here that this yellow line lines on top of the theoretical prediction, at least when you're above the mean field exponents. And so then we sort of think that this is quite convincing that the behavior of the excitation profile is indeed like was predicted by the theory. And this allows us immediately to get some interesting conclusions. So since this is the behavior of the tail, we can immediately conclude that some of the moments are going to diverge. So I remind you, the moments are just defined in this way. So this is the excitation profile, and those are the moments. And if the moment is sufficiently large, then it's going to diverge. So this is quite useful. Now, we cannot look on all the moments, of course, in a numerical study, but we do have a particularly useful moment in mind, which is the second moment.
Can I ask another question?
Yes, Achilles.
So this, if I interpret physically the way you start this, you basically start in an infinite temperature, if you want to call it state, right? Excite something and let it spread. So what if you did this for the ground state, for instance?
Yeah, well, I would, I mean, the honest answer, I don't know. I mean, I would expect it to behave the same. But this is guessing. Okay, at least the tail. Okay, what happens in the bulk, which we are going to talk about in a few slides, that's a different story. But somehow I would expect the tail to behave the same, and this is because we will see that the tail is in a sense perturbative, in some sense. So now I want to talk about a specifically interesting moment, and this is
another short question. Sorry.
Yes, yes.
So I understand that the non-interacting fermionic hopping problem has this power 2 alpha, but why is there no effect coming from the long Jordan-Wegener strings that you would pick up for the spin model?
Well, I don't know if there is no effect. I mean, or why would the effect be?
No, I mean, so what I'm saying is that if you took this non-interacting Hamiltonian that you have on the slide and put some integrability breaking term like interactions,
yeah,
one would imagine that because your spin chain does show gamma equal to 2 alpha, that would also. Now, this is not surprising in the sense that the fermionic chain with some interactions does not immediately do something different. But your spin Hamiltonian that you simulated without the next nearest neighbor term is not the same as the non-interacting Hamiltonian, right?
Yeah, sure. It's not the same. I mean, it's completely different model.
Yes, because of the strings. I mean, had it been nearest neighbor, it would have been the same. But
I agree, but I'm just giving it as an additional model, which I can study for quite big size, that can reassure to me that this gamma is not something weird. So I do see something which tends to this line, and this is the best I can do numerically. And I do see something which lies on top of the line for a different system. I agree. So this I think gives me quite certainty that that's fine, probably. Okay, so the moment that I want to study is the mean square displacement. So this is Q equal 1. And you see from this condition that we expect it to diverge for alpha larger, smaller than 3/2. So we can check that. So what you see here is this diffusion coefficient, which is just to remind you a derivative of the mean square displacement as a function of system sizes. And I plotted for alpha equal to 3 for different system sizes, and you see that that it nicely converges. Sorry. Another thing which I see from this plot, and this is what sort of helps me claiming that that the times that we study are not too ridiculous, okay, is that you can see that the diffusion coefficient appears to converge to well, I don't know if this is asymptotic, but at least it appears converges to a plateau. So to the best of what we can do here up to this quite short time 4, you see that you already converge to something which appears asymptotic. Okay, so this helps me explaining, and this is for alpha equal 3, where the system is quite local, so it's not too so the transport is not too fast. So for this system where we can go up to time 4, you see that we did converge to something which appears to be asymptotic, and this is going to be also my claim for smaller alphas. Now for alpha smaller than 1.5, you see, and it's not too small, it's like 1.3, not too small, but you see that already here there is a quite heavy dependence on the system size, which suggests that that the diffusion coefficient is indeed diverging, and we do have super diffusion here. So this was about the tail, and now I want to talk about the bulk of the excitation. So we were speaking about the tail here, and I want to talk about the bulk. So if I want to talk about the bulk, what is useful to see is how the bulk spreads as a function of time. So what you see here is the excitation as a function of time. Unfortunately, I didn't plot to which times it's plotted here, so I cannot tell you. But it's up to the maximal time, I guess, that we simulated. And what is plotted here with the dashed lines here, the alpha infinity limit, which I remind you belongs to just taking the local part of the Hamiltonian. And this local part of the Hamiltonian, in this limit, the Hamiltonian is diffusive. So basically what you see here, this is a numerical simulation, but you expect the profile to be roughly Gaussian. As you can see, it's not too Gaussian for short times, but it becomes more and more Gaussian for longer times. And what is more interesting is that the bulk, that this profile follows quite nicely the bulk of the excitation with the long range system. So what our conclusion is that the bulk of the excitation behaves as is described by the local part of the Hamiltonian, while the main contribution of the long range is just these power law tails. So this is basically the outcome here. So what does that mean? It means that we have the super diffusion like it was predicted by the simple picture, but this part here changes from diffusion to what we called an emergent diffusion. So what this emergent diffusion is basically something which has moments which are finite only up to some moment, and then they are infinite afterwards. So it has a bulk which is Gaussian, and then the power law tail. Okay, and this power law tail is just 2 alpha. So this is what we call emergent diffusion. Why we use the word emergent is because of that. So imagine that you are sitting at some distance from a perturbation which is coming towards you. So at the first time, you're going to see the super diffusive front, which is coming to you first. But if you wait long enough, you're going to see the bulk, which is diffusive. So this is why we call it emergent diffusion. But okay, man, that's just a name. So how can we model this? So one way to model this is by using this effective classical model. And so this is what you see here, just of course a master equation with some rates which decay as a power law in this way. So we can so basically what is this say is that we have some classical particle, and this classical particle can hop to quite long distances. So if we do that, if we do this calculation, then we can see that this is a numerical simulation of this master equation. So we see actually a behavior which is very much similar to what the quantum many-body system shows, is that we see, I mean, okay, this is the raw data. This is a data which is rescaled in a matter which collapses the bulk. And you see from this that indeed the bulk here for this system is described by just a Gaussian and the tail by this power law. So this simple classical model actually describes the behavior in the system, in the quantum system, quite well. And therefore, we can sort of propose, this is not a derivation in any way, but it's just by observation, that from the effective classical model, the prediction for the behavior of the profile is that there is a Gaussian dependence, and there is a transient, which is given by this form. And as a follow-up, we can, of course, calculate the time-dependent diffusion coefficient, and we can see that there is, at the end, if you take the time to infinity, it converges to just regular diffusion. But there is some quite long transient where it appears to behave a bit faster. So this is the story about transport. And now we are going to talk about, indeed, information propagation. And this is, so first I need to explain why I talk about information correlation in, or causality in non-relativistic systems. So we are going to start with something simple, which is relativistic systems. So in relativistic systems, we have a causal region, as we all know, which is given by a light cone. The information can only be inside the light cone; it cannot go out. And now the big question is how or why should we talk about causality in non-relativistic systems? And there is a naive way of thinking about it, but it gives the crust of why. So I'm going to present it anyway. And this is the example of random circuit. So we have an operator O, which is residing on some site, and all the rest are just unity operators. And we are operating on this operator by some propagator U. Okay, and we do it. Something here is on my way. Okay, and we are doing it. Do you see my mouse? I have no idea if you see my mouse now.
It's visible, yeah.
Okay, so we are applying it with the propagator from the left and from the right. And the propagator is described by this brick wall of operators, which are operating only on nearest neighbors. Okay, and the different colors are just describing is that the operators are random. Okay. Now they are random here, all over the place, but since I'm applying this operator from the left and from the right, the same operator, so this brick and this brick are of the same color and are the same, just conjugate. And the same about this brick and this brick, etc. Okay, so the picture is symmetric. Now you can convince yourself quite easily that if I write it in this way, then since this brick operates on two unities, we have U times U dagger, and this becomes unity, and then this becomes unity. And after I contract those guys, I can contract this guy. And if I proceed, I can contract all those guys which are residing in this light cone, and voila, I have a light cone in a system which is non-relativistic and described by those random circuit. It's a bit of a cheating, this description, but this allows you to at least to understand why this description, why one should even expect some notion of causality in non-relativistic systems. Now, how do we characterize this in practice? So what we do, we calculate numerically, and this time using exagonalization, what is called out-of-time order correlation functions. Specifically, what we measure, so for example, if I want to measure this light cone, the signal of this light cone, what I can do is I can look on how this operator spreads as a function of time. So at a given time, it is described by this set, for example, of operators. And I can see how this operator at a later time commutes with itself at time 0. Okay, so you see, you see that this in fact measures the signal of the light cone. So this is indeed what we do. So we calculate the, as I said, propagate the operator as a function of time and see how it commutes with an operator in a different position. And we expect, and we take the operator norm of this commutator. And this guy is supposed to be very small outside of the causal region and big inside the causal region. So this is the numerical simulation for a very similar system. And you can see that there are two interesting things here. One is for alpha smaller than 1, you see light cones which are not straight. They are bended and in such a way that the information propagates faster than normally. Okay.
Can I ask a question?
Yes, Achilles.
Is this the model that you showed earlier, the spin model that you showed earlier?
Yes, it is. It is essentially the same model. I think the only thing is that here is also a ZZ term, and it was missing in the previous model. And when alpha is larger than 1, so this becomes also quite interesting. Is that the light cone is actually very straight. Okay, so this is different thresholds of the signal. Okay, so this is different basically lines where this signal is the same. So it's like topographic lines, and you see that it starts curved, but then it straightens up. So we see that for alpha larger than 1, the effect of the long range is actually not there. It's you cannot see it. I mean, it only appears in the tail, which I'm not showing you here in this picture. So that's all what I wanted to say about clean systems. And unless there are questions, we have 20 minutes to talk about disorder systems. Questions? No? Okay. So let's start about disorder systems. And since I guess, I don't know, I mean, I'm not looking at the audience, but I guess not everyone know about many body localization. So I'm not going to assume it and talk about short range systems first. And what you see here is a model, a spin model, which is short range. It has a flip-flop term. It has a magnetic field, which is random this time. And it has a ZZ interaction between the spins. Since I'm coming from Israel, as you can see, it is very nice for me to explain this model in this way using dreidels, which we use in Hanukkah, which comes in a month or so. But basically, it describes just spins which rotate along some precess along some axis. Now, what we know about this model, there are a lot of things which we don't know, but roughly we know is that if we change the disorder strength, then the system exhibits a transition. And the transition that it exhibits is a transition between a thermal state to a non-thermal state, namely a system which thermalizes for weak disorder, stops thermalizing for stronger disorder. And in terms of transport, it was at least believed when this theory was conceived in 2006, that the system transitions from diffusion to being insulating. But then it was shown in a number of works that it is actually behaves more like subdiffusive. It is still debated by some people whether this subdiffusive transport is finite or not. But at least at the moment, most, I would say, studies, including experiments, suggest that transport is subdiffusive. And what we wanted to see is what happens. I mean, firstly, I want to talk about a little bit about the subdiffusive transport and where it comes from, and how does it mesh together with long-range interactions. Why is it interesting to study this regime together with long-range interactions? So that's the first motivation, is what is the mechanism, or at least what is the mechanism that people believe is of anomalous dynamics. And the mechanism is commonly known as the Griffiths picture. Basically, it is described again by a master equation where there's a particle which hops around, and it has a finite probability to hop across barriers, but this probability to cross across barriers decreases exponentially with the height of the barrier. Now, this model, which is was studied many times, I mean, I would assume that the first one who studied it was Dyson in the 60s, but I'm not entirely confident about that. It was studied to death by Shlomo Alexander in the 80s, who has a lot of analytical results about this model here. And then this model was used much later by the Harvard group to explain the subdiffusion. So basically, what is the intuition? The intuition is very simple. You have a particle which is hopping in one range. It has to hop across barriers. This is the disorder barriers. And since if you want to see this particle emerge on the other side of the picture, it has to cross all the barriers, no matter how high they are, and no matter how rare they are. And now there is a competition of two things. One is the probability to have a high barrier, which is said to you is exponential in the height of the barrier. And there is another thing which is exponential, is the transition rate. And you can calculate the average transition time, which is this. Well, it's very simple. This is just the average over this 1 over W. And you can convince yourselves that there are two regimes. One, when this alpha, which is, again, it's very phenomenological. All this model is phenomenological, by the way, of course. So when alpha is larger than beta, then this integral is converging and you have just plain diffusion. But when the opposite happens, when beta is larger than alpha, then we have subdiffusion. That's a bit harder to see. I mean, this transition time diverges, but you can actually derive it, and this is what Shlomo Alexander did. And well, that's what I wrote here. And this model basically describes phenomenologically, again, or explains why we have subdiffusion in one-dimensional disordered systems. Now, if one wants to believe this picture, then one needs to see what this picture predicts in other scenarios. And one prediction, I'm not going to talk about all the scenarios, but one of the predictions is that when there is higher dimensions, there is diffusion. And the reason is, imagine that you are like in New York, for example, and you're a particle which is wandering between high scrapers, and now you're not blocked anymore by those high scrapers. You can just go around, okay, like it's plotted here. And since you can avoid rare blocking regions, then there's no reason that they're going to stall you, and you're getting diffusion. So this was actually studied this was studied, and also there was an experiment about that. But I'm not going to talk about 2 dimensions here, and I'm going to allow the particle avoid these high scrapers or the blocking regions by adding long-range interactions. Okay, so now the question is, does subdiffusion survive long-range interactions? Okay, when we add long-range interactions, now we can hop far away. And at least from the Griffiths picture, one would predict to have diffusion. And we will see that this is indeed the case. I mean, for the Griffiths picture. So let's start with transport first. So the model, okay. So I want to actually first generalize the Griffiths picture. So this is easy to do. So we do something which is very similar to what we did in the clean case. So this is a master equation of the particle, and this is the exponentially small probability when the barrier is high, and we add to it another ingredient, which is the decay with the range of the hope. Okay, so now we have long range hopes, not only hopes on this one-dimensional lattice, but we can hope also far away. And
quick question.
Yes.
This Hij has an exponential distribution.
It doesn't really matter. I mean, what does matter? So the shape of the distribution doesn't matter as long as it's unbounded. Okay, if it's unbounded, that's fine. But we used an exponential distribution here.
And then is that also true for sort of the conventional Griffiths picture that you presented, that the V there doesn't need to have an exponential distribution and it's enough as long as...
Yeah, it's true. Yeah, you can use any distribution you want as long as it's unbounded.
But what do you mean unbounded? As in...
So the number can be as high, the barrier can be as high as you want, not bounded by 10, for example.
But so for instance, a Gaussian would also work, even though
Gaussian,
it's
it will. But this is the distribution of H, right? The transition rate is exponential, right? But the distribution of this guy can be anything as long as it has a long tail. Well, not long tail, unbounded. So this is what we use here for this model, and now you can see that indeed we get diffusion, and we do it in the same. So let's look on this plot first. This is something which you've seen before, so it should be more familiar to you. This is the density rescaled such to account for diffusion, and you see that the bulk indeed is collapsed and gives you a Gaussian, and there is a power law tail of -2 alpha. Okay, like we had in the clean case, in fact. Okay, so adding disorder to this model doesn't do anything in terms of the model. You can add it, you can put just one here, and it gives you the same result. But it might take a bit time to get to converge the diffusion coefficient. You see, you need to go to quite long times, but the exponent gamma of transport is very close already for short times. It's very close to diffusion, very close to 1. So this is what the generalized Griffiths picture predicts, as I guess expected. Now let's see what we get numerically. Okay, so this was a model. Now let's see what we get from our model. So in our model, we use this Hamiltonian. This Hamiltonian has now a z term, unlike the clean case, and a long range. Okay, and the random magnetic field. Okay, and we study it again using this method, which I must say again, for long range systems, there is no choice. You have to use matrix product state, otherwise you never can get this tail. So this is a must to use large system sizes. And here you can see that since we added disorder, we can go to larger time somehow. Still short, of course, but a bit longer. And you see here plots for various disorder strands, and the main reason of these plots is just to show you that the power law tails are still there. Okay, and in fact, they are not dependent on a disorder strand. Okay, so this is actually nice. So the tails do not depend on disorder, and in fact, I would maybe say that it's expected because disorder lives locally, and the tails are sort of like far away from the perturbation. So that's maybe more expected. Now, what is less?
The dashed line that you had there is the same exponent that you would predict for the clean case.
Yes, exactly. It's this 2 alpha. So in this case here, we don't have anything surprising, I would say, but let's see what happens to the bulk, which is more interesting. So now, what we do here, in order to, since we don't have a lot of time, I'm showing you only the diffusion coefficient. So so here you have, let's start here. So this is the mean square displacement as a function of time for a long log plot. And it is plotted for a various alphas. Here, I don't know why only 3 are shown in here, but of course, I mean, this is various alphas, and you see, and you see that it looks power lawish. Okay. Now we can extract this power law by calculating the log derivative. Okay, this gives us this slope. This gives us the slope of this of those lines, and this is what you see here as a function of time. Now this is very noisy, as you can see also from here, from the perturbation. So it's not an extremely good measure. We are going to talk about a better measure in the next slide. And you can also see a diffusion coefficient which appears to decrease. But again, here it's also quite noisy. You cannot escape here because the raw data is very fluctuating. So well, this data shows us that there is some transport which it has a power law behavior and becomes slower when you increase the alpha. It is not extremely conclusive, I would say. So since this is the case, we wanted to look on an additional quantity, which behaves a bit nicer. And this quantity, so now we are moving again to information, and this quantity is not the talk this time, but entanglement entropy. Now, I think I can probably safely skip this slide here, which defines the entanglement entropy. And I'm going to present the results here. So now you see that this looks already much better. So entanglement entropy, which is a non-local quantity, it averages much larger portion of the system, and then those fluctuations that you saw before in the mean square displacement, they go away, and the quantity behaves much nicer, much cleaner. And now we can extract, so first of all, we can plot the entanglement entropy as a function of time, and you indeed see that it behaves as quite clean power law. And to see it more precisely, we again calculate the exponent lambda here as a function of time, and you can see that it converges to something which is smaller than 1. Okay, so for a diffusive system, one would expect this to be 1. For subdiffusive system, one would expect delta to be smaller than 1. And you can see that you do see something which looks sort of like a plateau. So one can envision how it is asymptotic, and it is smaller than 1 clearly. And another evidence of that is to look on the derivative, just the linear derivative of the entanglement entropy. And one can see that this derivative decreases as a function of time. So again, it suggests that the behavior is slower than linear with time. So this, now what we wanted to do, another step to sort of like convince him and more, is to compare those exponents. One question one can ask is whether there is some kind of relation between the exponent, the dynamical exponent of the transport, this gamma, and the dynamical exponent of the entropy delta. And this relation was proposed, I think, first time here in this paper by Vosk, Hughes, and Altman in 2015. it is known from a review that I wrote with David that this relation doesn't hold very good. So it doesn't really hold nicely, but it does give at least some qualitative behavior. And this is what we do here. So we use this relation and we define a quantity z in this way. And this is done in order to plot those two exponents on one axis. And this is what you see here. So what is plotted is 1 over z, but one time it is computed from the transport, and you see, so this is this exponent here. And you see indeed that it is super noisy. I mean, for larger alphas, it becomes like crazily noisy, almost as the signal side. This line here represents the asymptotic behavior for a local system, what is known for local systems. So you see it indeed converges to this local system as expected. For the entanglement entropy, the behavior is much less noisy. It's much less noisy, and you see that it also converges to the asymptotic value, and they roughly have a qualitatively similar shape. Okay, I mean, they do not match, as is already known, but they sort of behave the same. So this gives us, okay, so this is for the alpha. Now, if you plot it as a function of the disorder strength, then we have something which is quite similarly decaying. Now, what we conclude from here with some confidence is that there is a subdiffusive transport here. It is emergent because there is still this tail, this power law tail of super diffusion, which arrives first. But then again, if you wait long enough, you have a subdiffusion, which comes. So this is, I remind you, in contrary to predictions of the Griffiths picture. So we are exactly on time because I'm on my last slide. What I have shown to you is that for clean systems we have a scenario of what I call an emergent diffusion, namely that you first see a super diffusive front, and after this initial super diffusive front, a diffusive front arrives. So asymptotically, or at least formally, if you take time to infinity, then you would call this transport diffusive at the end. For disorder systems, we have an emergent subdiffusion. So if you combine those two things together, what one can sort of conclude is that the system has two types of behavior. One behavior is the which is dictated by the long range, and this is those tails. And in a sense, it is weak because it's only transient. But the main behavior of the system is described by the local part of the Hamiltonian, at least if one wants to talk about a transport or information spreading. So this is kind of surprising, so that the effect of the long range in this sense is quite weak. And another thing which we showed is that there is some kind of inconsistency, at least if one believes our conclusion about subdiffusion in long-range disorder systems. There is an inconsistency with the Griffiths picture, so it is pertinent to try to understand this inconsistency and to try to see whether maybe the reason for subdiffusion in short or long range disorder systems is something else and not this phenomenological description. And I'm done, 2 minutes over time, but done.
All right, thank you. So are there any questions?
Have you done quasi-periodic systems using your method?
Yes, you can. We, in fact, we studied that. Quasi-periodic systems are, well, we studied that, and we decided at the end not to publish. I don't know, maybe it will be published at some point. But it's a bit hard because it is you cannot average very well, so the data becomes very fluctuating, and it's very hard to get conclusions. So, for example, you must know that there is currently basically two beliefs, let's say, about transport in quasi-periodic systems. Is one belief is that this is ultimately diffusive. One belief says that it's subdiffusive, and I would say that there is currently no good evidence in either direction. So it's a bit because just because it's very hard to average, and sort of like everything looks quite messy. Anyone else?
So I have a tangential question. You know, there's this phenomenological model that doesn't work, with the master equation, the classical model with these nearest neighbor hops, which are exponential and blah blah. So, I mean, do you have any idea what classes of models can actually be described by such a model? What I have in mind is really, well, the question I really have in mind, which isn't actually related to your talk, I'm afraid, is whether I could have systems which are sort of non-ergodic for other reasons, for example, constraints, and whether I could model them with that thing. Do you have any idea, or I mean?
I have no idea. I mean, currently I've shown that this model is not working, at least for disorder systems. So, I mean, I don't know, maybe sometimes, I mean, since I don't understand the reason why sometimes it works and why sometimes it doesn't work, so it doesn't help much. Maybe the reason that it works, maybe the reason it works is just by coincidence, but maybe, I mean, I don't know.
Yeah.
That's the problem with phenomenological problem. Yeah.
I had a related question. So, what if you simulate? Okay, I mean, maybe you have done it. What if you have a model which is just free fermions hopping with long range, and you add a small amount of disorder?
Well, so this was done. This was done by people. It is, as far as I know. I'm not a big expert there, but there are works by Merlin about this, and well, many people actually. I mean, but a lot of works by Merlin, and as far as I know, it is known to be diffusive. I mean, there is a threshold where it becomes localized, but I'm not talking about here. But when it's delocalized, it's known to be diffusive.
Yes, I mean, I think the localized it gets localized at alpha in your language at alpha equal to 1, I think, for one dimension.
Yes,
if I'm not wrong.
Yeah,
but so then okay, so in that case, if it becomes diffusive, like your Troy Griffiths picture would predict, I mean, your Troy Griffiths picture would also predict emergent diffusion, right? If I understood correctly.
Yes, it predicts diffusion.
So does it not mean that it's just that the Troy Griffiths picture is good enough for this free fermion hopping with long range hopping with disorder, but not good enough for this spin system with interactions?
I wouldn't be very confident saying that, because I mean, the fact that you have a model, a phenomenological model, which works in one case and doesn't work in another case, doesn't mean anything, right? I mean, okay, it works here, it doesn't work there, but what do you learn about that? I mean, unless we understand why it works.
So, I mean, okay, so the reason I'm asking this is, in your model, do you know what happens if you switch off the SZ term? But with keeping the disorder in place.
We didn't experiment that much. I mean, that I think this wouldn't change much. What is more interesting question is what would happen if you only keep the ZZ term and you switch off the hopping, the long range hopping on the flip-flop term. That I think would be much more interesting question. Unfortunately, we didn't study that, so I don't know the answer. The reason that this is the reason why this is interesting is that now your particle cannot hop, right? I mean, the spin cannot hop far away, but the energy can. So it could be an interesting situation where you have a transport of spin, which is very different from a transport of energy or information. But we didn't study that, so this is a speculation.
But would you agree that in that case, if you have only the flip-flop term, which is short-ranged, but the ZZ interaction is long-ranged, the spin transport should be massively suppressed?
With the ZZ term or without?
Yeah, with the ZZ term being long-ranged, but the flip-flop term being on the nearest neighbor.
Yeah, the transport would, well, I would expect it to be suppressed, yes. But in terms of in which sense suppressed? In terms of this long range tail. So for example, I wouldn't expect maybe to see long range tails in transport of spin, but I would expect it to see in other places.
You mean like energy?
Yeah, but I'm not, I mean, this is guessing here, right? Because it is, I mean, it is suppressed in a sense, but still, even the spin has a projection on the energy, right? So it's not that they are orthogonal, the operators. So it is possible that there is still some effect, but it is much weaker.
But
that's why this is that's why this is interesting, right? Because you can't just say, well, this term. No, I mean, I'm saying this is why this is interesting, because you can't just isolate the effect of the ZZ.
Yeah.
Is,
no,
right?
It's clearly interesting. That's why I'm saying that I'm a bit annoyed by myself that I didn't do it. But I mean, you have finite time doing stuff, so.
But
Yeah,
then
it is interesting.
But if you have strong disorder, like you had in your, or suppose I make the disorder in your model strong, then wouldn't it be the case that both energy and spin should have suppressed transport? Because then does it not become a question of the basis in which this system is trying to be localized? And then if the interaction in that base, or the interaction which is diagonal in that basis is long range, then it will give some rigidity to the state. And
I think there are two effects. One effect is that the ZZ term is orthogonal to transport of spin, right? So in a sense, this is one effect. It has nothing to do with localization. So this is what you asked before. And the other effect is what the disorder is doing. So this is another effect which indeed suppresses everything. So of course, if you include disorder, and this we did study, right? The dependence on disorder, indeed you see that everything becomes suppressed. The transport and the information transport, everything becomes suppressed, as you would expect.
Yes, I mean, I was wondering if it so happens that at say fixed but high value of disorder, if you then increase the range of the ZZ term, again, everything becomes suppressed or not. I mean, yes, of course, if you increase disorder, things would get suppressed. But I'm saying that hold the disorder fixed, but increase the range of the ZZ term.
Yes.
Then I would expect that everything would again be suppressed with the range of the ZZ term.
Even more.
More, yeah.
Yeah, sure. I mean, I would guess. I would guess that even when disorder is present, the ZZ term somehow suppresses in the transport. But I mean, all those things are made to be studied. I mean, my guess is as good as yours here. That's yeah. That's about that. Okay.
Maybe I have a general question about the subdiffusion.
Yeah.
So what do people think, like, what are the implications of subdiffusion for the eigenstates of the system?
Oh, well, that's a very hard question. I don't know. I mean, it's. I mean, the reason it is hard is that I mean, I don't think there is a very solid opinion here. So there were some people think that in the subdiffusive case, the eigenstates are basically chaotic in a irregular way, so nothing interesting happens there. Some people think that they are not, So they're actually sparse in a sense in the Hilbert space, right? So they're multifractal. I mean, it was not studied very well. I mean, there is a study, basically, I mean, well, how many studies are there? Like 2 or 3 studies about the multifractality of eigenstates in the XXZ model. It is not, I wouldn't say that it's super conclusive. I mean, the risking, you know, advertising myself, I mean, in the study with David, we use quite big system sizes to study multifractality of eigenstates, and it appears that the eigenstates in the subdiffusive region are not multifractal, at least in the basis that we considered. So we considered the computational basis. And this is actually might be very important. And this is something which we are examining right now. I mean, in your study with Maxime and Dima, you consider the different bases, and you do appear to see multifractality, and it is I think important. So this is something which has to be understood more precisely, because it is not inconceivable that transport and multifractality of the eigenstates are connected. As we well know, they are connected for the single particle case. So it is not unimaginable to see them connected also for the many body case. But unfortunately, this connection is not very well known, or at least not very well, I would say, established. And that's a very interesting question, like whether they are connected, if it is multifractal, on which basis one should look. So all this, I would say, is kind of open, not heavily studied in the community.
All right, any other comments or questions?
So I have one question. So can you go back to the slide with the generalized Griffiths?
Yes. The moment is okay. Here it goes. Generalized Griffiths. This one?
Yeah. Okay. Yeah. The other one after. The one after, basically. Okay, never mind. I mean, so the question was, can you modify your, I mean, okay, so what looks to me that is missing from this classical picture is the fact that not only there is some, not only that the particles can hop, or the single particle here can hop, but also the fact that there can be other particles with which it interacts, and which sort of try to, how should I say, repel it. So is there, can one come up with some kind of a classical picture where there is not one particle but many particles, and then there is some, so if moving one particle means that you have to rearrange some of the other particles to, I don't know, minimize is probably not the right word, but keep the energy fixed, then that causes some additional slowing down of the dynamics, which leads to eventual emergent subdiffusion in your, like in your.
Well, I would assume that the answer is yes. I mean, this model is just well, I don't know if it is the simplest model one can think about subdiffusion, but it is one of the simplest ones, the random barrier model. So this is why it was chosen. It also sort of like intuitively matches to what can reasonably happen in the system. But you can of course imagine various other things which will result with subdiffusion, and one of them being kinetically constrained models, right? So for example, if you put enough kinetical constraints, then one can have situation where transport is slow. I mean, this is one of the way it models glasses, as you know, classical glasses. So one can think of such models, of course, but I mean, I mean, the main problem with phenomenological models is that you only can test them with predictions, right? Since you cannot derive them, so that's the main issue. And currently, the Griffiths picture, it was nice at the beginning, but somehow, like on the predictions, it's not delivering so well. If you try other models of subdiffusion and try to see how they work in in high dimensionality in long range, maybe they work better, but I don't know. But then you'll have to, in order to convince, you'll have to test them on additional scenarios, of course.
Yes, I mean, but maybe because this classical model gives you something which is different from what you get from the quantum model is clearly insufficient, right?
Yeah, well, it tells that that's the model is probably too simple, or at least fails in this case. I don't know, or maybe it has to be adjusted in some way.
Yes, and I was just thinking that maybe one simple model which gives you subdiffusion is and which looks like coming from some long range interaction is to put some other particles and have them.
Yeah, one can do that, but I mean there are many ways one can have subdiffusion. For example, you can put the particle on a fractal and you can get subdiffusion. That's another way to do it. I mean, and then also that at least physically can sort of explain what one sees in the numerical experiments. And in fact, this also works in a sense in higher dimension, right? If the fractal is of certain dimensionality, then one can have subdiffusion on the fractal in higher dimensions. I don't know how one would sort of cook this up with long range. That's a bit harder. But maybe it's also possible. I don't know. I mean, the main point is that there are many models one can cook up, but the main problem is how do you check what is good and what is not.
All right. I at least have to go pretty soon. So.
Okay. So we're chatting with you later, right, Achilles?
Yeah. Just you can call me later. In fact, Stidadi has to go as well.
Okay.
Right, because we have a meeting with someone soon.
Okay.
So I am going to sign off here, I'm afraid.
Okay, good. I mean, we still have 9 people.
But yeah, you and I can talk later. But yes, if other people want to ask, let's start.
The number of people dropping exponentially.